Good morning. I am Ružina Bajci, and I am professor of emeritus, which is meaning I have nothing to do all the time to read and bug you and ask questions and so. Anyway, it is my real pleasure to introduce and be the host of David Fridovich-Keil, who he was my teaching assistant at Berkeley, so this is how far we go. And then he also took a room in my basement at one point of his life. So we really developed a very close relationship, talked about all kinds of things, including game theory and mathematics. I was told what to say, so here I have to read this. Previously recorded talks can be found in our YouTube channel and website. If you are joining us via Zoom, please submit your question using Q&A button at the bottom of your screen. These will be answered during the Q&A panel. At the end of the talk, if you are here in person, you will have an opportunity at the end of talk to provide your questions to the panelists, through the panelists. And we have two students, panelists. One is Bruce Lee and Igor Spisoyevich. I think I am probably the only one who can pronounce it properly, being of Slavic origin. All right, so let me just tell you, David has been working with Claire Tomlin. Claire Tomlin was his thesis advisor, and they were looking at how to model interaction of two robots using game theory, which there were several other people who have done similar work, right? And yes, yeah, you probably will mention them, Lily, and with Shankar Shastri and so. So as for the future, please tune next Friday, April 19th and 10:30 to our next GRASP lab on robotics featuring Christy Morganson from University of Washington. It's interesting because Lily is also from University of Washington. She also did work on this game theory. For more information on upcoming events, be sure to follow us on social media or check out our website. Don't spend too much time on social media. It's not good for you. It's really not good for you. Yeah. Thank you again and have a wonderful day. This is the instructions from the above. Anyway, David is a delightful guy who really has a deep ingrained curiosity, which I really appreciate. And sometimes you may have heard me complaining that some of the students don't have enough curiosity. And David and I shared a lot of interesting things about culture, about different people, and history, in addition to all of the sciences. So enjoy his talk.
All right, thanks so much, Rujna, for a really kind introduction. And thanks to all of you for having me. So I want to tell you, yeah. Yes, we did. Yeah, so I was Rujna's TA, the lab TA for the intro robotics course. And so I remember, creating all these lab assignments and inserting bugs just to make the students, think about what was actually going on and figure out how to fix them. So yeah, that was the first time I think we actually really interacted, and it's been great. Okay, so what I want to tell you about today is a topic that I think has really captured my imagination since I first first encountered it back in maybe 2018 or so. And at that time, what was happening was I had previous exposure through my PhD with Claire Tomlin in solving zero-sum games that modeled robust control problems. So we were interested in, say, making sure a quadcopter could reliably track a trajectory and exactly characterize the margin of error it might have when tracking that trajectory, so that we could make a hard guarantee, hey, this thing is not going to hit the wall or whatever. And so I was familiar at the time with casting that kind of problem as a zero-sum game played over time between the protagonist, myself controlling the quadcopter, and the antagonist, nature, injecting some kind of disturbance over time. And then what happened in the summer of 2018 was I went to intern at a self-driving car company, and I was working on motion planning, and I got there, and they basically told me, hey, this is the algorithm we use to do planning. We solve some kind of MPC problem, and that's how we do it. And then we have this gigantic software stack that does some fancy perception and predicts where the rest of the world's going to end up in the next few seconds, and then we try to react to it via model predictive control. And so we had all these problems that I was dealing with, and what essentially all of them, from the planner's perspective, boiled down to was a mismatch between what we predicted would happen and how we reacted. And so we were basically spending all day long trying to fix those kinds of mismatches. And then the predictor would make some change. That team would push a new feature. It would break everything we did, and we'd have to react. So we had this joke that was, hey, prediction, you guys should just predict what we're going to do at the same time, and then the planner, we can just go home. You can fire all of us. So I kind of was thinking about this through that summer and realized they were actually right. So really what was going on was that the planner and the predictor, these were solving problems that were being treated sequentially. Let's predict what's going to happen based on what we saw over time, and then let's react to it. That was a sequential process. But really, it was neglecting the fact that what we plan to do will influence what others see in the future and how they'll react. And so the actions we choose to make in the future are going to impact what we see in the future, and so we can influence other people. And you had to treat that problem in a coupled way. And so that got me thinking about in-player interactions, framing them as games that are non-cooperative perhaps, and how to solve this problem. So I kind of went to my boss at the time at this internship and said, hey, I think this is the right way to think about this problem. And he was like, yeah, sounds good, but I don't know how to solve any of those problems. And so that's kind of why I've been working on it for the last 5 or 6 or how many years since 2018. So, okay, so that's a long-winded way to say, I'm going to try to tell you about some algorithms to solve games efficiently, or at least these specific types of games. And what the real theme of the talk is to kind of show you that the algorithms that you use to solve these particular problems encode something about the information structure of the problem itself. And by information structure, I mean, what information does every player have access to when they need to make a decision? So this will all hopefully become clear throughout the talk. It's a bit of a tutorial, and then you'll kind of smoothly see research topics coming in. So that's the plan. If I can get this thing to work. Okay, well, we'll just do this. So, great. Perfect. Okay, so I've told you about how I encountered these game problems in terms of autonomous driving. That's obviously on the left. But if you're not so interested in driving, the same kinds of problems arise all over the place. So in particular, I've become recently interested in like aircraft routing as another instance of these problems. I'd love to learn more about power flow. I think the same kind of models will appear there too. But anyway, for the purposes of this talk, I just want to keep traffic as the running example. So we'll be thinking about traffic problems as kind of the natural instantiations of these games. And if you're thinking about traffic, if you're working at one of these companies like I was in 2018, you'll be thinking immediately about model predictive control as the kind of paradigm for planning, for decision making. But in this talk, we're going to be talking about games. And so you can think about like a model predictive gameplay as the natural end player extension of model predictive control. So how does this all look? Basically, if you are right here, if you're this particular car, and you're trying to figure out what to do in the next few seconds, what you probably want to do is think about some function j that maps your trajectory, your states x and control inputs u to a number. And you want to minimize that number. You probably have to satisfy some constraints. So here I just wrote down some physical vehicle dynamics constraints. That's that first one. Maybe you need to satisfy some initial condition. Maybe you know exactly where you are and what your vehicle state is. Anyway, you want to solve a problem that looks something like this to determine the optimal trajectory to follow. But in reality, that trajectory is going to depend on what other vehicles in the scene are doing. So in particular, a really easy way to see this connection would be to look up at that objective and realize that what the first car thinks of its trajectory depends on what it predicts those other two other cars in the scene are going to do in the future. That's what I've highlighted in blue. Okay. So where does a game arise? Basically, the game theory kind of framing of this problem would be to say, okay, well, those blue things I highlighted before, the trajectories of cars 2 and 3, well, really those are themselves, they arise from optimization problems that are faced by those drivers. So driver 2 and driver 3 are solving the same kind of problem that we, the autonomous car number 1, are trying to solve. And all of our variables are kind of mutually coupled. And the coupling, I've written it down in terms of the player's objectives. Maybe it arises in constraints too. But anyway, as soon as you take this perspective that the player's decisions impact one another's objectives, you have a game. Okay, so this is, I think, a pretty natural way to see these things arising. Let me tell you a bit more about, just what are we looking for when we talk about these games. So any of these games, I'm talking about games that are played over time. So every player, obviously has an objective that they're trying to minimize here. There's a state of the game. The state changes every time step. Every player has an action that they can make at every time. There are rules of the game, dynamics to the game. So if it's a vehicle, these are just kinematics or dynamics. If it's a game of chess, it's obviously the rules of chess. And then the kind of critical part that I'm going to focus on for most of this talk is the information structure. What does every player have access to when they have to make a decision? So we'll see a lot more about that later. And then the final question is, what do we look for? So given, if I tell you all 3 of these things, what kind of solution am I looking for? So in this talk, we'll be talking about Nash solutions, but I'll actually kind of allude to a few other solution concepts at the end. The bottom line is, for a Nash solution, we're looking for a point in the strategy space where no player can unilaterally improve. Okay. All right. Let me instantiate this a bit. So if we're in one of those traffic problems, maybe the dynamics are just given by the some model of the vehicles. So you could keep track of whatever states you think are important for that model, positions, headings, etc. You could model every player's objective as maybe like a linear combination of preferences that I've alluded to here. So like staying in the lane, maintaining a speed limit, avoiding other avoiding collisions, things like that. And maybe you can model the information structure as state feedback. So maybe say every player gets to observe the full state of the game, whereas every other vehicle when they make a decision. All right. These problems have been widely studied for a really long time. And I find the history quite fascinating. If anybody wants to learn more about this book is quite good, especially the first chapter or two, I think. But anyway, this theory all goes back to a man named Rufus Isaacs, who was publishing tech reports for RAND back in the late 40s and early 50s. And I think I just can illustrate the basic idea of this early work in kind of two quick kind of little brain teasers. So the first one, I think he called it something like the nuclear bomber problem. But this is late 40s, early 50s. So you can imagine what was going on at the time. And there's a bomber that's trying to drop a bomb somewhere in this near this country. And there's a fighter. And the idea of the game is how can the fighter shoot down the bomber as far away from this country as possible. And the bomber wants to do the opposite. The bomber wants to drop its bomb and get shot down as close to the country border as possible. So anyway, what's happening here is if you think about it, and you kind of make very simple assumptions about how the planes can move, you'll realize that there's a very nice geometric solution to this problem. And this is the kind of thing that Isaacs was, Isaacs' examples were like particularly elegant about, is that he could often find some very nice embedded geometry to the problem. So in this case, what you do is you basically draw the perpendicular bisector to this line and realize that, okay, at that red point, this is the point at which the bomber and the fighter can get there at exactly the same time if they're moving the same speed. And it's the closest of those points on the bisector to the country. So basically, the best thing for the bomber to do is to just go straight for that point. If the fighter does anything other than go straight for that point, the bomber could get closer. And so basically, the best thing for them to do is just make a beeline there. And Isaacs basically proves that if they do anything other than that, it's exploitable. So there's a nice geometric solution. Another kind of classic problem with a nice geometric solution is called the homicidal chauffeur problem, where in this case, it's a lightly disguised version of a missile guidance kind of scenario. But basically, there's a car that's trying to run down a pedestrian, and the car has a heading angle. The pedestrian can run any direction they like. And there's, again, this very cute geometric answer to how can the car best run down the pedestrian. Anyway, so Isaacs basically came up with this theory to describe these problems. And because it was essentially the early 50s, there was not much computation to speak of to solve them. So he was reduced to basically finding simplified cases that afforded a nice geometric answer. And in the general case, what do? Basically, what you do is, and he realized this, is that the kind of global feedback equilibria of these problems are characterized by coupled PDEs. And because there was not much computation at the time, he resorted to geometric solutions, although he did characterize properties of solutions to those PDEs more generally. But nowadays, we can do a bit better job of solving these problems, but we still hit, issues of cursive dimensionality and become unhappy pretty quickly. So this is where I guess the real meat of today's talk starts. What do we do? Like if you are faced with these issues, what can you do? And I'd say the answer that I want to kind of put forward is that you can look for other kinds of solutions. You can look for local solutions. So how do you solve these problems locally? So the way to do this is to think back to those coupled optimization problems I wrote down at the very beginning. So if you write them down like this, kind of the first intuitive thing that people did was basically to think about some kind of iterative scheme and try to say, well, if players 2 through n have fixed their strategies, what can player 1 do? What's player 1's best response? And then player 1 can declare, this is my new strategy. Player 2 can say, okay, well, given everybody else, what do I want to do now? And you can kind of repeat this process. Maybe you can randomize the order. There's all kinds of variants. But that's a pretty intuitive thing that people started doing very early. The issue is that at least naive versions of this have convergence problems. So you can even just think about rock, paper, scissors as like the classic simplest example of where these kinds of things will fail. If I say I'm going to play rock, then of course somebody else will say they're going to play paper, and now I don't like rock anymore. I'm going to play scissors, and we're just going to end up cycling around and around and around. So there's obviously a lot deeper theory here, and there are cases where these kinds of schemes will work, but let's see if we can do something a little smarter. So think back to these problems again. And if you didn't see the for all I, and you just saw like one version of this optimization problem, I guess what would be your knee-jerk reaction of how to solve this problem locally? Who's taken an optimization class? Nobody. Really? Okay. How about a constrained optimization class? Yeah. Okay. How about like a little bit more detail, but sure. Okay. Somebody's taken it already, but it's not even necessarily convex. Okay. All right. So that's an algorithm. That's good. But what would you look for? Like, how would you know that you found the right answer? Or like, how would you write down that algorithm? Like, what's it trying to do? Okay, I'm looking for 3 letters. 2 of them are the same. Yeah. Okay, you basically write down the KKT conditions for this problem. And then you'd try to construct an algorithm that's satisfying those conditions, and then maybe you check the second order conditions too. All right, so here you can do the same thing. You can just write down the KKT conditions for every player and stack them all up. And so that's what I did over in the bottom right. And notice, I guess I'm being a bit intentionally careful here to just include equality constraints. So I don't have to worry about complementarity conditions or anything like this. But we can talk more about how to handle those if you like. Anyway, if you write all these conditions down, you get basically a big function of the states for all the players, the actions for all the players, and this variable lambda, which is just the Lagrange multipliers for all the constraints. And this big G thing, you can see how it's made up, but basically you can think of it as just some fairly arbitrary, smooth, nonlinear function of all those variables. And well, to first order, if I satisfy G equals 0, if I can find XU lambda that satisfy this equation, I must be simultaneously satisfying all the players' first order conditions. If we squint and don't worry too hard about the second order business, then we're at a Nash solution. So it turns out, basically that's something you can do. You can try to like use a root finding method, Newton's method or something, to solve this system of equations. It could be wildly nonlinear. Maybe you have to be very careful with line searching and trust regions and so forth, but you can do it. And if you do, you'll find something called a local quasi-Nash equilibrium. The local, just because it's based on gradients information. Quasi-Nash, just because we're only checking we're not checking second order information. So basically, we're looking for critical points for all the players. Don't worry too much. Basically, this is a local version of a Nash equilibrium. Okay, so if we kind of take it for granted that for whatever problems of interest, a Newton-style method will work for that kind of scheme. Here's the interesting question to me, is suppose I do all of that. Suppose I'm looking at this problem and I've solved it with whatever variant of the algorithms I just discussed. What is this inherently encoding about the information that each player knows when they have to make a decision? Let me put that another way. When I solve this problem, I get a trajectory for every player. I get a trajectory of the game, and I get a sequence of actions for every player that satisfies their optimality conditions. In order for a player to actually execute that strategy, what information about the game do they need to know when they're playing it? Like imagine this is a game of chess or something. Any ideas? The rules? Sure. Yeah, they need to know the state of the board, do they? You'd hope. But do they? Yeah, key. That's key. Okay, so what's happening here is if we solve this, we kind of get an equilibrium trajectory for the game in terms of the states. An equilibrium, like we get state at time 1, state at time 2, state at time 3. Those are decision variables. So if we solve the problem, we have a sequence of states that will hit along the equilibrium trajectory. We also get a sequence of controls. So in order to actually execute those controls, all you need to know is what time it is. And then you can look up in your sequence of controls, okay, well, my watch says it's time 3, so I'm going to play control at time 3. And the state trajectory will follow the dynamics of the game. So that's got a name. This is basically an open loop strategy that you're solving for. And for anyone who's got any kind of feedback control experience, this is kind of immediately problematic. Okay, so what do I mean? If you think about an open loop strategy, it's like at the bottom. It's a bit unfortunate, the naming scheme, I think, but if you want to think about what is an open loop strategy, it's basically a strategy that you can play with your eyes closed. Right, basically, if I've got an open loop strategy to like walk across the stage and get out of the room, all I need to know is the sequence of steps I'm going to make. So I'm going to walk this way with my eyes closed. But of course, I don't know exactly how far it is to the stairs. And so this is a terrible idea to close my eyes while I'm doing this. So an open loop strategy is a function that maps just the initial condition, and maybe it's indexed by the time, the subscript there on gamma, to an action. A feedback strategy is one that you kind of need your eyes open to play. You need to be able to see the state. So it's a map from the state and the time to an action, right? Eyes open, eyes closed. Let's see an example. Why does this stuff matter? Here's just a very toy example of a game where player 1 is starting from the bottom right, and they want to get player 2 to go to the origin. Player 2 is starting from way up here, and player 2 wants to approach player 1. Player 2 just wants to be close to player 1. Both are lazy and don't want to apply a lot of control inputs. You can think of this, you can kind of write these objectives down as quadratic functions, and maybe let's imagine that the dynamics here, the rules of the game, the dynamics are like cars driving, so there's a heading, and players can choose their turn rate, something like that. I've shown you an open loop equilibrium and a feedback equilibrium in different colors. Any guesses as to which is which? By the way, both are unique in this case. Blue's open loop. Why? Overshoots what? I mean, it doesn't even get close to the origin. Like this guy's not even, it's more than it's overshooting. You're right, actually. Blue is open loop. But I wouldn't really think about it as overshooting anything. What's happening here, so what's happening here is that in blue, player 1, that's the bottom guy, knows that nothing it ever does will get seen by player 2, because both have to choose a strategy which only depends on the initial condition and the time. So player 1 knows that nothing it does will ever influence player 2. So because player 1 wants player 2 to go to the origin, it can't influence that component of its cost, but it can certainly choose a small control, which means it can not yaw at all. And since it started moving that way, it's just going to keep going that way. Similarly, player 1 knows that player 2 knows that player 1 started oriented this direction at a certain velocity, and basically is just going to make a closest approach. So that's the open loop equilibrium. And the feedback one is maybe the more intuitive thing. It's player 1 knows that Player 2 is going to get to see the state in the future. So player 1 knows, if I go towards the origin, player 2 is going to want to get close to me, and we'll both end up at the origin. So that's why green, you see them both kind of driving towards the origin. Okay. So another example, let's say I'm working at a self-driving car company and I want to make my car be polite to others. How can I encode that kind of behavior? Well, I can basically penalize my car for other players' control effort. Right? So if they have to decelerate very quickly, they have to apply a large input, then I can penalize myself for that. So like maybe this is a dumb way to do it. I can take whatever cost I had, this J1 tilde, that just depends on my input and the state, and I can add some norm of player 2's input. In open loop, this is not going to influence the equilibrium at all. And here's why. All you need to do is write down the optimality condition for player 1. So I basically write down their Lagrangian, take its gradient with respect to their primal variables. And I see that this term, basically the norm of player 2's input has no dependence on either the state or player 1's action in open loop. So that derivative is 0 and it disappears. So that's why basically, if I try to be smart about encoding politeness this way, it's just not going to work. So I have to be more clever. In feedback, though, that derivative will not disappear, because what's going to happen is that player 2's action in the future depends on the state in the future, which depends on player 1's action now. So that derivative with respect to player 1's action now is non-zero. Okay. So all this is basically pointing to the fact that the structure of information available to the players can really influence the equilibrium. And if you naively just follow your nose and write down the KKT conditions and go for it with whatever algorithm you like, you could be missing something important. So what is feedback actually doing? Let's be a bit more careful. So if you think about a feedback equilibrium of a problem, it could be an optimal control problem, a game, regardless. You are basically saying that you need to satisfy a time consistency property, a strong time consistency property, which I think is best understood as just the existence of a dynamic programming solution. So if you write down like a kind of an extensive form of a game or just a tree, what this is saying is you need to be able to work your way backward from the bottom to the top and construct players' optimal strategies or equilibrium strategies that way. And if you do it that way, you'll automatically be satisfying whatever feedback conditions you require. There's another way to understand all this, though, which is also, I think, pretty useful, which is in terms of what's called information sets. So if you look at a kind of textbook on this, what they'll often do is they'll augment the kind of tree structure this way and start adding sets that look like this. And the idea here is that every boxed state or set of states is just the set of states. It is a set of states which a particular player cannot distinguish among. So in particular, a feedback information structure is one that looks like this, where the players can distinguish exactly what the state is at every time. Okay. An open loop information structure would be this one, which is to say, at time 1, both players know what state it is, but at time 2, they have no idea what state it is. All they know is what time it is. So at time 2, you see that the red box includes both possible states, which is saying that the players can't tell which one they're in. They can't distinguish among the states in that box. Okay, so sometimes that's useful to imagine. Mathematically, what is this? Well, let's assume, just for the sake of argument, that players' objectives are, sums of other functions over time. I can then kind of just transcribe that exact condition of strong time consistency this way. And I can write down at some arbitrary time, little t, player i's strategy as a function of the state at time t. And I can write it this is going to look very familiar. This is essentially me just unrolling like a Bellman equation. And I can say, well, it's the cost that I accrue right now plus the optimal cost to go in the future for each of these sub problems. So right now and in the future, we have to satisfy dynamics of the game. satisfy the rules. But crucially, in the future, I have to be also satisfying these kind of like, I have to be choosing actions according to these optimal strategies. Like I can't just choose any action I like. And so these boxed constraints, these are very important. These are the things that encode feedback equilibrium structure, right? So in other words, actually what happens is if I remove those boxed constraints, everything will collapse and we'll get back to exactly the problem I was saying, well, you can stack up the KKT conditions and find a root and everything will be fine. So if you remove those boxed constraints, we get back where we were before and we'll get back to an open loop equilibrium. All right. So, right, this is where we were. What's happening? I'm saying that the thing on the left, this is player I's strategy at time t as a function of the state at time t. I'm saying that, well, this itself, this is a function. It's implicitly defined to be the solution map of an optimization problem, and it's recursively defined. So that means that there's a lot of nesting going on. And it's no surprise because I was drawing out this tree earlier. So there's a lot of nesting in a tree. It's exactly the same. And so if there's capital T time steps to this problem, you can look in the top of the sum, then there's that many levels of nesting. And at each level, there's n players and they're all coupled together. That's what's happening here. So I'm saying the action for any player other than I must be equal to the output of its strategy. Okay. All right. And so think back to writing down KKT conditions for, this problem. If you're going to write down the KKT conditions for this ridiculously nested problem, it's going to get gross very fast because what you're going to need to do is encode derivatives of all the constraints with respect to the primal variables. So, well, when you transcribe this, you're going to need to write down a Lagrangian. That's going to assign multipliers to all the constraints, and then you're going to take the gradients of the Lagrangian with respect to the primals. So you're going to end up needing those kinds of derivatives. But they, in turn, they're recursively defined. So to evaluate this derivative, you need the first derivative of the strategy for all the players in the future with respect to state in the future. This is all nesting in a very gross way, which means that you need T orders of derivatives to do this right, which is going to get horrible. So in practice, what you can do, and this is it's taken us a while to get here, but what you can do in practice is just approximate it. Just pretend that all the players are going to have to follow affine strategies. And if you do this, all the high order gradients information disappears. And what's neat about this is if you follow your nose and write it all down carefully, this algorithmically looks a lot like sequential quadratic programming, which if you've taken your optimization class, this is like a classic way to solve any equality constrained optimization problem, convex or otherwise, and arrive at a local solution. There's all kinds of great literature to ensure that you are always finding descent directions towards local solutions. I mentioned line search and trust region methods. Those are some of the classics. You can also handle inequality constraints. There's all kinds of good methods for this. So we were very excited to realize that basically making that exact approximation gives you something essentially sequential quadratic programming for these feedback problems. And the other cool thing is that when you kind of write down the kind of algorithm block diagram, everything is very easy to do. And it all relies on being able to solve a linear quadratic version of the game, linear dynamics and quadratic objectives. And that happens to be something we've known how to do since the earliest reference I know of is 1969 that solves that problem. It's a version of a Riccati equation to solve it. Okay, so it's very fast to solve. And it actually works. So you can do this. This is just like a quick Monte Carlo study that we ran very early to just see how well it worked. So you can just cook up an example. This is 3-player game. Everybody's trying to cross a crowded hallway without getting too close to each other. And what we did is just started from 500 random initial strategies for all the players. And for each of those 500 things, just run the solver for 100 steps and see what happens. So if you do that and cluster the results, just kind of k-means kind of thing, you immediately see 3 clusters. And so here I'm just showing you the trajectories of in each cluster and the corresponding like convergence of every run. So convergence is, very reliable. The clusters, each equilibrium, it seems to be 3 equilibria of the problem. And they're encoding extremely intuitive behavior. In the first one, the players are, outer players are kind of hugging the wall and letting the middle guy sneak through. And in the others, they're mirror images of each other where middle interchanges place with one of the top or the bottom. So this was encouraging. Also, kind of one of the most fun things I got to do near the end of my PhD was to try to like put an early version of this algorithm on a test aircraft just to taxi around an airport, avoiding runway intruders and things like this. So we posed all this as end-player trajectory games and solve them easily real time. And so anyway, kind of watching that happen was super fun. Okay, so where do we get? Multi-agent interactions are very natural to write down as dynamic games, but the information structure that describes those interactions is very subtle, and it arises in these weird ways in the solvers that you build. So if you build a naive solver, you can end up solving for the wrong equilibrium. And as we saw in that example of like driving towards the origin, they can be wildly different. You can have wildly different equilibrium solutions depending on the information available to the players. And if you choose a solver that goes for the wrong solution, I don't care how fast you run it. You can run this in a receding horizon loop as fast as you like. It's always going to be wrong, and you'll never end up going the correct direction. So that's I'd say like the major message here. If you know what information is available to each player, even if it's got this nested structure to it, there are nice approximations that we show you can make that allow for real-time computation. Okay. And I was kind of talking about an early version of this work back in like 2021 at an RSS workshop, and it was kind of especially neat to see that the speaker right before me is from Waymo, and they were actually trying something pretty similar on their car. So I guess the point I'm trying to make is just that these ideas of modeling interactions among drivers on the road, it's something that people in the industry care about too. And they had done their own version. I happen to know a little bit more detail about it that I can answer some questions offline maybe, but there were some subtle differences between what they ended up trying and what I just showed you. Anyway, all right, so I think we've got just enough time to talk about this. So I want to, now that we understand a bit more about what these games are, what they look like, and maybe some of the kind of key ideas in solving them fast, let me pick on the dual problem, the inverse problem. So everything we just talked about assumes that all the players know everything about one another's objectives. That seems kind of unreasonable in a lot of circumstances. Like if I'm driving on the road, how do I know exactly what lane change somebody else wants to make? Or how distracted they are, and maybe they are gonna not even see another player because they're on their phone or whatever. So we've thought about this problem, and some of the I guess work we've been doing in the last couple of years has been trying to show conditions under which you can infer those objectives from watching strategic play. So here's an example of 5 cars on the highway. It's obviously simulated, and we see imagine you see like a noisy measurement of all the cars' position over time for a few seconds. Can you back out all the way to the left, like what were the players' objectives? What were their, so here's a heat map of, some components of their cost. So the way we've kind of developed to think about this problem is to think about it as an estimation problem. So there's some parameter of the objectives that we don't know, and we would like to estimate from data. So, the simplest starting point would be to think about just some kind of maximum likelihood, map estimation problem, whatever you have. But basically try to maximize some measure of observation fidelity subject to the constraints that correspond to equilibrium conditions. So basically, we know that these cars are behaving strategically. We know that they are trying to optimize for something. We just don't know what it is. How can we encode the fact that they are optimizing for something when we're inferring their objective? So we basically just embed that as a constraint. And if you transcribe what are these things actually, well, if it's a maximum likelihood problem, I want to have some kind of sensor model that allows me to establish the likelihood of a measurement from the vehicle's state and maybe what they're doing. And we just showed how you can transcribe equilibrium conditions into equality constraints or maybe complementarity constraints in the more complicated situation. So here, those are the open loop KKT conditions for all the players, and you can just stick them right here. And if you do that, you end up with just a non-linearly squares objective with these potentially wild non-convex equality constraints. But sure, you can still deploy your favorite root finding algorithm to solve this problem. So if you do that, what happens? Like again, presuming the algorithms work appropriately, you can get them to converge reliably. Then we were interested in understanding what is this added structure of the strategic behavior assumption actually buy you for estimation. And so we cooked up exactly that kind of highway driving example I showed you before. And the punchline is that if you don't really do much, don't really use this assumption that the players are strategically optimizing for these unknown objectives, you're very susceptible to noise. So that's what this plot is showing. Kind of the observation noise is on the horizontal axis, and the kind of prediction accuracy, estimation accuracy is on the vertical axis. And you see that, it's a log scale. You see that you quickly get separation between these kind of existing methods that don't account for the game theoretic structure and the problem I just showed you. If you solve the problem I just showed you, even though it could be horribly non-convex and you're finding a local solution, we'll basically squeeze more juice out of the data. Think of it almost like adding a prior. So exactly, the point is basically these game theoretic models can add nice prior information for estimation, I would say. All right, let me just show you a couple other kind of quick outros before we close and take questions. So the thing I just showed you about maximum likelihood estimation, I think the obvious question that I had for like a year or two after this work was, is there a better way to handle kind of distributional uncertainty? Is there like a Bayesian take on this? The short answer is, well, yes, you can do this. But what you have to do is be able to account for, wildly non-Gaussian distributions on the unknown game parameters. And to do that, fortunately, there are, machine learning tools to do this, right? So we just basically coupled like a variational inference technique that is super common in generative modeling with a version of the game solver I just showed you. And that solver, we also showed that you can implicitly differentiate its solution with respect to the game parameters. And that was the kind of additional missing piece. And because you can do that, you're able to kind of stick it in as a layer in a neural network and diff back through it. So kind of train the variational autoencoder with it. So the kind of short version of all of that is to say that here I'm showing you an example with an intersection. There's two vehicles, and the unknown parameter of the objective is which point in the intersection is this player's desired goal position. And we basically allow that hidden parameter to just be a point in R2. So it's continuous, and what the neural network has learned to encode is a distribution that basically says, okay, well, if they're in this configuration, I know that this car either wants to go somewhere in this lane or somewhere in that lane. We do this from a bunch of data of watching people drive, and then just show how you can couple a planar to it. So So that's one thing you can do. Another thing that's I think is kind of interesting is to say that you can, so most of the first part of the talk was showing you how to encode feedback structures. Well, you can also do that in inverse problems. So we showed how you can take that maximum likelihood problem and basically just erase the constraints and replace them with the much more complicated KKT conditions of the nested feedback problem and simplify them to a level where a solver can actually handle it. So we showed how you can do that. And then the other last thing I want to mention is that all of today's discussion has been about Nash equilibria, either in open loop or feedback settings, but we can basically play the same games, same tricks for solving Stackelberg problems. Stackelberg equilibrium concept is kind of encoding a hierarchy among the players. So here I'm showing you up here just that player 1 influences player 2, who influences up to player n at time 1, and then at time 2 it's the same thing. So there's an order of play, and those kinds of problems you can immediately see that they're also nested, and because there's still nested problems, we can start to play exactly the same tricks to solve them. And you can even do inverse problems there. You can even try to infer what the hierarchy is among the players by watching them play. So that's also work we've been up to recently. I think let me close here and just tell you like the big punchline of that last line of work. Most of what we've said is just that a lot of the algorithms here are enabled by the fact that equilibrium solutions of games are at least directionally differentiable with respect to their parameters. So, and kind of goes back to high school calculus. So anyway, that's all I had, and I'd love to take questions.
Thank you. Thank you for the talk. So question, on the Stackelberg equilibria, how would you suggest we think about sort of these formulating these like hierarchical games versus doing something like a hierarchical reinforcement learning setup? Are they fundamentally different problems, or should we think about them just as different formulations?
I guess I would go back to you. It's like, to me, are they different problems? That's the first question. And I guess I don't know exactly which hierarchical reinforcement learning problems you're thinking of, but if they're the same problems, then I would say they may have particularly different structures that or properties which make different algorithms more or less sensible. So, for example, everything I've showed you has been a deterministic problem, whereas typically in reinforcement learning cases, you're interested in stochastic dynamics and maybe stochastic policies. So if that's an important character of the difference, then if that's an important distinction, then that should have some impact on the algorithm you choose. Or another thing would be, often in reinforcement learning, algorithms are designed so that they typically don't require like an analytic model of the dynamics or the constraints or the objective. Like if you talk to a reinforcement learning purist, I think they'll kind of want you to design an algorithm which doesn't require foreknowledge of those things. Whereas everything I've showed you has basically been assuming, hey, yeah, I know exactly what the dynamics are and I can differentiate through them. I know exactly what the constraints are, et cetera. Yeah, I don't know if that helps, but yeah.
Sorry, George, to build off of maybe the partial observability work, your environments are all assumed to be static. If your environment were to start changing and they not be agents that are changing.
Yeah.
So let's say you have boats and now you're in some type of flow setting. Does that feed into these dynamic game formulations well? Is there a constraint there that maybe you didn't talk about, but that it would fall into it naturally?
Okay, sorry. I think what you're getting at is, can the dynamics of the game be time varying? Is that essentially what you're asking?
Yeah.
Yeah, so look up there, all the Fs, those are the dynamics, and I've subscripted them with time. So you can have whatever arbitrary time dependence you like. Yeah. I mean, you have to know what it is, but yeah. Yeah. Yeah.
Thank you for the talk, first of all. Just out of curiosity, So I was wondering whether you considered this corner cases where open loop strategy can be a best response to a feedback strategy.
Oh, that is a good question. So
Like I can think
Yeah.
of, for example, a
Mhm.
couple of examples. Let's say I'm a crazy person and I just want to. So I'm on the road, on highway, on a straight road, and I want to arrive at the destination as soon as possible.
Yeah.
And I say, hey, my gas pedal got stuck and I pulled off my wheel.
yeah,
Okay. And I communicate that. I say, oh, like stay away from my way and otherwise we will crash. So the best response to that, such a open loop strategy, as far as I can see, is just stay away from the way.
yes. So if somebody declares an open loop strategy, then there's no reason, I mean, assuming the problem is deterministic, then there's no reason you would need feedback information. So you're totally right. But the equilibrium you would find would not be a feedback equilibrium anymore. So I think all you're kind of getting at is like, well, what if the game is actually just not a feedback game?
But I can assume that I'd say if it's two-player games, you're
Yeah.
right. But if there are multiple players, then
Yeah.
it could be still some of them needs to play open loop strategies.
So it is possible that an open loop strategy, actually, hold on. Yeah.
Strategies.
Hmm?
Excuse me. So I think it's possible for some of them to play open loop strategies and some of them to play feedback strategies.
Let me not say something wrong, but the concern I would have is whether an open loop description of a strategy, sorry, okay, let me back up for a second. There's a concept which goes by the name of a representation. So you can have two strategies which, when evaluated along a particular state trajectory, always give you the same sequence of controls. So those would be called representations of one another. So think of them like a description of an equivalence class. So if you knew the equilibrium trajectory of the game, you could certainly construct an open loop strategy which recovers a player's actions along that trajectory. But that representation of the trajectory, my sense is it would not satisfy strong time consistency. So that would be my immediate concern, but don't quote me. Okay. Yeah.
Okay, we'll go with one from Zoom. Edward asks, can the insights here be used to analyze single agent scenarios? So for example, in model-based RL, could you view the joint optimization of learned dynamics and the policy as a game?
What was the first part of the question?
Can the insights here be used to analyze single agent scenarios?
Oh, I would say yes, but in single agent scenarios, things are a lot simpler. So in particular, in single agent deterministic scenarios, you can prove, it's actually very easy to prove, that the open loop solution, the trajectory of the open loop solution exactly recovers the same trajectory as the feedback solution. So that's why if you think about it like an LQR problem, you can write down a Riccati recursion and get back all the feedback controllers and then evaluate from a particular initial condition and get a trajectory. You'll get the same trajectory and the same sequence of controls as though you just written down a quadratic program and solved it. So, so what I would say to this question is basically that in the single agent setting, as long as it's deterministic, you don't need to worry about all this garbage about feedback so much, as long as you're writing it down as an optimization problem like this. Now, things get more subtle if there's stochastic dynamics or observation noise or things like that. Maybe that's what the question's getting at. Yeah.
I'll ask the dual question. Can you give us a sense, David, of how things scale with respect to horizon and number of agents?
Yeah. So good question. I guess I don't actually have this written down as like what would a Newton step look like, but let me not bother winding back the slides, but basically what you would do is you'd write down the KKT conditions of this problem, and then you'd, like, if you're taking Newton steps on those equations, the complexity would essentially be determined by how hard is it to solve for a Newton direction on this. So basically, you need to solve a linear system of equations to get the direction that you're going to step all the variables. That's what determines the complexity. And basically, that complexity is the same as you'd get in any optimal control problem, in the sense that, well, in the worst case, it's kind of cubic in the size of the matrices involved. So in what's the size of the KKT system, it's the number of variables, right, on each, more or less. And so that's, basically going to be like, so that the size would be linear in the number of players, because, the number of controls and the number of states would be linear there, and then cubic in that. But there's, so anyway, it's still polynomial, but there's sparsity, which is nice. So when you write down the Jacobian of the KKT conditions of those things, it actually has a nice banded structure. And so you can exploit that. So it's actually not quite as bad as cubic. There's one other thing I was going to say that I forgot, but yeah. But the point is, it's polynomial. Oh, time horizon. Yeah, so just like a Riccati recursion, you can basically have this clever matrix factorization that makes everything linear in the time horizon. Yeah.
There's a second part of Edward's question from Zoom. It says, on open loop versus closed loop strategies, we find that open loop deep neural policies tend to generalize better than closed loop policies. By ignoring the inputs, they naively ignore all distribution shift errors. What are your thoughts on addressing generalization or bringing insights into deep neural network policies?
Wait, so the premise here is that a deep network that's mapping from the initial condition to an open loop sequence of actions is going to generalize better than something which is mapping from the state at any given time to an action at that time.
Yes,
I generalize in the sense of if I change the dynamics a little bit or something like this.
Yes, I believe so.
I guess I'm not, this is a surprise to me. So I guess I don't have any particularly intelligent thoughts about it, but I guess I would just say I'm surprised. Yeah.
Thank you.
Yeah, but I'd love to learn more about it if there's a reference or something.
One question for me, are the GTs assumed to be like strongly convex in the use? Like what if, for example, the arguments have multiple solutions?
Oh yeah, I'm glad you asked. There's as you could imagine, there's a lot of caveats. I skipped a lot of details. Right, for example, I never even told you like what this thing would exactly converge to. So yeah, your question is like, what if this argument is generally a set, and I've kind of naively written as though it's a singleton. So yeah, so in practice, you totally don't need to require everything to be like strongly convex. And what'll happen is, as you're solving these, so as you're solving this problem, what's going to happen is that if something is not strongly convex, you'll end up like Newton will find you a solution, whatever regularized version of Newton you choose. And we've just been rolling with that. So it's maybe not a particularly compelling, like fully fledged answer, but I would say numerically speaking, it's not a problem. Yeah.
I guess I could also ask one. If you're in a setting where there's a collection of agents following some optimal policy,
yeah,
and then you introduce some new agent, could it simultaneously learn the objectives of the existing group and then play some optimal policy itself?
Yeah, so there's something, so I guess there's maybe both active and passive versions of that question. Can somebody like actively suss out what is this other guy, new player trying to do, and then react? That's a much harder question that I think I've not seen any like particularly compelling good answers to, although it's interesting. What we have done is address the passive version of that, which is to say, let's say that I've got some buffer of observations I've taken in the last few seconds, and I'm also trying to plan what to do in the next few seconds. What you can do is write down a version of that problem, where here what I'm saying is, instead, just imagine that sum over time to be like time from beginning of my observation buffer to the present. But imagine that the constraints are dealing with states and controls from the beginning of the buffer through the present into the future. So if you do that, what you're saying is that I'm trying to be faithful to the observations I've received in the past, which include something about this other new player. The constraints are saying every player was acting strategically in the past, but they're also saying they're going to continue acting strategically in the future. And the theta variables that were kind of the unknown parameters of their objectives, including the new player, those influence both the past and the future. So you can kind of predict, I mean, literally in the NPC kind of sense, you can predict what's going to happen in the future and couple it automatically to your estimation of the past. So you don't have to like separate estimation and control in the same sense. Yeah, sure.
So when we are assuming each agent will reach a Nash equilibrium policy, how well do that apply to what happened in reality, say in the actual highway application? Because there are K-level game theory, which means not everybody is the perfect rational person who can consider indefinite amount of policy iteration. So how well does it apply in reality?
Yeah, so the question's basically, are these Nash or other equilibrium concepts really accurate descriptions of how people behave? And yeah, unsurprisingly, like a lot of people have asked this question over decades. And so the short answer is, yeah, there are different equilibrium concepts that do try to account for like bounded rationality or kind of other issues here. So just one that comes to mind is there's some nice work it came out 3 years ago maybe, that was addressing like a bounded rationality equilibrium concept. So what you can do there is you can say, take the original Nash problem and then also imagine that every player gets to select a stochastic strategy and give players a bonus for acting randomly. So some measure of like the entropy of their strategy or something like this. That, subject to whatever distributional assumptions you put on it, that thing can have a very nice, clean equilibrium condition. And you can solve it kind of with similar Riccati recursions. So, I mean, with, again, a lot of caveats, but that's a paper I remember that was kind of trying to address that issue. My own take would be to really do justice to that question requires probably more data and more experimental ability than, I or probably most other academics would have. So there's data sets out there for, recording like Waymo cars in different intersections or whatever. But the trouble is that those are pre-recorded. They're not like I can't go in there and say, well, what if I had done this other different thing than what the car actually did in the data set? So I don't have the counterfactual. And I don't know of any data set that could possibly have that information. So people try to train, neural network models to predict other players' actions, and then it's kind of a chicken and the egg problem. So I've kind of been very unconvinced by, like, generally the outlook in that space. So anyway, long story short, I've like thought hard about that problem and come to the temporary conclusion that I don't want to think about it anymore. And I just want to trust the decades of people in economics and other game theorists that have concluded that this is a decent enough model. Yeah.
Okay, we have another question from Zoom from Austin that says, how stable are the computed policies when other agents play non-optimal policies?
How stable are the computed policies when players deviate from equilibria? So, yeah, so this is a great question. I guess the real answer to this question is they're very stable if this is a zero-sum problem. If this is not a zero-sum problem, then they can be exploitable. So, yeah, that's the answer. Yeah. Oh, let me actually say one more thing on that. If it is a zero-sum problem, it's probably not too hard to imagine that if player one has a nice, beautiful convex objective with respect to its variable, I mean, depending on the situation, it's probably not hard to imagine that player two's objective becomes concave if they're wanting opposite things. Depends, but that can cause numerical problems. So I would say like the methods I've shown you are not, like they're looking for first order stationary points. And so they can be susceptible to kind of curvature issues that really arise in zero-sum problems. Yeah.
Thank you, David. This was typical David. Yeah. Thank you. Very, very substantive, but limited.
Okay, well, thank you very much.
Yeah, yeah.
I try not to overclaim anything.
No, I cannot ask any reasonable question except that saying, what are the limits of these game theoretic approaches?
Oh, there are so many limits. So many limits, like where to start. The first place I would start is like everything I told you about is a local solution. So, yeah, I would never use, like, even if we could solve zero-sum problems perfectly, which I just described have issues. Well, even if we could do that, we're only finding a local solution. So I would never, just go and tell you, hey, this solution is robust to arbitrary perturbations of the problem, because like I would never go and use this for a safety critical situation.
So you have a life chart on
Yeah.
work with much more complex systems.
Yeah.
Using this.
What's that?
Using this technology.
So what was the first part?
Well, that you plan to look at some more complex systems.
Oh, yes.
Situations using the same methodology.
Yes. So for example, I mean, like one of my students just now is working on algorithms which are not so susceptible to the numerical problems I mentioned in zero-sum cases, just as an example.
All right. Thank you very much for all of you coming.
Yeah. Thank you. Well,